And then we will start now. Okay, so today we are going to, so in the last class, we ended the class with, the last 10 minutes, we went over uh, the next topic to be discussed, which is resonance theory. And that's what we are going to be learning today. This is a really important topic because a lot of the reasoning that you will be doing and a lot of the concepts that and reactions that you need to understand in organic one, they will need the skills of really understanding resonance theory. In addition to that, you're going to be learning the curve arrow symbolism with resonance theory, which is something you will use for reaction mechanisms. So let me repeat again a couple of the ideas that I went over in the last class so you guys can understand what this topic is about. So I'm showing a molecule here, and I want everybody, once again, guys, get the notebook at home, write everything with me. So that will that will make things easier for you to understand writing and taking notes and like following these ideas. Okay, so I'm drawing the Lewis structure of this molecule here. Okay, I'm gonna ask you guys in the first place, what is the hybridization of this oxygen atom here? So what's the hybridization of that oxygen? Good. So that oxygen has a double bond, so it has a pi bond. Clearly, it's an sp2 hybridized oxygen. And then I'm gonna also ask you, given that it's an sp2 hybridized atom, I'm gonna pull a question right now, which is where in which orbitals are the lone pairs residing? Say, so I want to ask you guys, and I want everybody to please answer to that question. In which orbitals are the lone pairs of that oxygen located? So where are those electrons? And I'm giving you several options there, sp2ps and sp3. So that we all agree that this oxygen is sp2 hybridized, but I want to make sure that you guys understand what that means. Okay, so we have 15 people still to respond. Please complete the answer. Okay. All right, so remember, so most people seem to know the right answer, which is sp2 hybrid orbitals. Remember, guys, how we reasoned this. So we said an sp2 hybridized atom obviously will have three hybrid orbitals, three sp2 hybrid orbitals, because we are combining 1s and 2p. That's a total of three. So three sp2 hybrid orbitals, and it's also having one p orbital, obviously, because that p orbital is the one that is not being hybridized, right? So that's how we reason this. So that's those are the surrounding orbitals for an sp2 hybridized atom. Okay. So how many sigma bonds do we have in that oxygen? How many sigma bonds do we have in that oxygen? So there's one sigma bond, meaning that one sp2 hybrid orbital will be used for that sigma bond. Mm-hmm. How many pi bonds do we have in that oxygen? There is, that is correct. We have one pi bond, And we know that pi bond are side-by-side overlapping of p orbitals. So the p orbital of that sp2 hybridized atom is used for the pi bond. And then obviously then the two remaining sp2 hybrid orbitals must be occupied by the lone pairs. Okay, so that's the answer. So remember that the bond angle between these lone pairs will be slightly larger than 109.5, sorry, than 120. Okay. All right. So meaning that once again, guys, we have a sigma bond through a sp2 hyperorbital. We have two lone pairs in sp2 hyperorbital, and there is a pi bond through the p orbital. Okay. So that's this pi bond. So that's okay. So what about this carbon over here? What is the hybridization in this carbon here? Guys, what's the hybridization of that carbon? So that carbon has, so how many pi bonds do we see in that carbon? One pi bond, right? So if it has a one pi bond, what is the hybridization of that carbon? Certainly it is sp2 hybridized, guys. Some people answer sp3, so that's a little concerning, okay? Once again, for sp2 hybridized atoms, we have three sp2 hybrid orbitals and one p. And it is sp2 precisely because there is a pi bond. Because there is a pi bond, there must be a p orbital for that pi bond. So three remaining orbitals to be hybridized because carbon is in the second period of the periodic table. Valence shell is shell 2, 4 orbitals. One is safe for the pi bond, so you're hybridizing the remaining three, 1s and 2p, sp2. We went over that extensively before. So how many sigma bonds do we have in this carbon here? How many sigma bonds in this carbon? There are three sigma bonds, and I have three sp2 hybrid orbitals. So clearly, I have in that carbon three sp2 hybrid orbitals that are made the result of this carbon using sp2 hybrid orbital for those sigma bonds, and there is a pure p orbital for the pi bond with the oxygen. Okay, correct. So now I'm going to move on to the next atom, which is going to be the oxygen. This oxygen over here. So that oxygen, what's the hybridization of that oxygen, guys, of this oxygen here? So that oxygen we said in class before that is sp2 hybridized, and the reason for that is because it's an atom with lone pairs, which is next to an sp2 atom. So every atom with lone pairs next to an sp2 atom will be sp2 hybridized, and then following the same reasoning here, I'm gonna ask you guys in which orbitals are the lone pairs of these oxygens residing. How many sigma bonds do we have in this oxygen to begin with? How many sigma bonds do we see here? So you have two sigma bonds. So clearly there are two sp2 hybrid orbitals that will be used for this sigma bonding, and then there is two lone pairs. One lone pair will be then located in an sp2 hybrid orbital, and the second lone pairs will be in a pure p orbital. Okay, so that's how this is very important for you guys. I really hope that you understand how relevant it is for everybody here to identify the hybridization of these atoms, and also to be able to tell the orbitals that are surrounding these atoms, the orbitals that these atoms are using for bonding and for lone pairs, because that's the only way you will be able to really reason um, more complex problems in regards to the electronic structures of these molecules later on. Okay, so this is a very, very important thing to really know well, and something that we have discussed in class, as I just said, extensively. All right, guys, so according to this picture, and I'm gonna just draw the orbitals, I'm gonna make a simplified draw here of that molecule. So according to the analysis that we have just finished right now, we just agree that there there is, I'm gonna remove the oxygen atoms just for the sake of simplicity, because I'm gonna just use it, the backbone of the molecule, to show the orbital. So We just agreed that there is a p orbital in this oxygen because it's sp2 hybridized. There is another p orbital in this carbon because it's sp2 hybridized, and there is a third p orbital in this oxygen because it's also sp2 hybridized. Okay. Okay, so now that's a different question. Amna. Okay, so my question is, once again, we just reason this, and according to the reasoning, there are three p orbitals in these three atoms here, right? One in the oxygen here, one in the carbon for this pi bond, and that is one here. How many electrons in total in these p orbitals? And I'm gonna pull this question because I think that's also a very important question. So how many electrons in that? How many electrons in total? How many pi electrons total? I want you guys to think about the answer. What's the total number of pi electrons that we have in that system? It's also a very relevant thing to reason, and hopefully after today's class, everybody will know this well. So how many total number of pi electrons we have in that system? Okay, come on, guys. No, no, Ruth. So one of the answers is being given. How many total electrons we have in that system? I want everybody to answer that question because I want to get a sense of how many people are really understanding this problem. So 11 more people to go. Please just finish answering. How many electrons in this system? So then the answers are basically half and half for 3 and 4 electrons. 8 people are not responding, so I'll take note of that. A few who are not responding might not be paying attention. I really don't like that. Guys, please pay attention. And you need to answer these questions. Okay, I'm gonna close the poll now. Okay, guys, so I want you guys answer now a different question for me, and that will hopefully clarify this question that I just asked. How many electrons do we have in a pi bond here? How many electrons are composing a pi bond? 2 electrons are forming a pi bond, 1 from each p orbitals, right? And how many electrons do we have in this third p orbital? 2, right? So what's the total number of electrons? 4 electrons. So we have 2 electrons in this p orbital here, a lone pair, and we have 2 electrons in this pi bond. That's a total of 4 electrons, okay? That's important also to really understand. Okay, guys, so now that we have agreed on that, if you look, and I'm gonna just copy and paste this oh, I'm sorry, this structure that I just drew here. This is the Lewis structure that I show you guys. So if you look at this Lewis structure that I drew on the board, right, and you look at my orbital analysis here, we define a pi bond as a side-by-side overlapping of pure p orbitals. So in this case, I do have 2 p orbitals that are parallel, properly aligned. So that's what we call a pi bond, which is reflected in this Lewis structure with this double bond. However, I also see 2 pure p orbitals here side by side that must be also overlapping, right? And I don't see in my Lewis structure right here any indication of that interaction in between these 2 p orbitals. It's everybody can see this, right? So there are 3 p orbitals next to another, right? And my Lewis structure here is showing a pi bond here, but there is no any indication in my Lewis structure of a pi bond in this area over here. However, I do have in this carbon and in this oxygen two p orbitals parallel and next to one another. So if to me a pi bond is side by side overlapping of properly aligned pure p orbitals, I see that we have a problem here. And the problem is that this Lewis structure is not really showing us the real structure of this molecule. And once again, the reason for that is because in the real structure of this molecule, there must be some type of pi bond character in between these two atoms, which is clearly not reflected in the single Lewis structure that I presented on the board. Okay? Does everybody understand that? Or if you have any questions, if you didn't understand what I just said, please ask, because this is really the foundation of everything that we will discuss today. Okay, so I gave you an example once again in which uh, the orbital analysis led us to understand that there were three p orbitals next to each other, properly aligned, and my single Lewis structure is showing pi bond only in between two atoms, not in between these two. Obviously, I cannot, in this same structure, I can't just add another pi bond here, because if I do that in this structure, I'll be showing 5 bonds for this carbon, and we know that's totally and absolutely impossible. So the bottom line for this is that this is a system which we are going to call a delocalized system. And a delocalized system is any molecule or ion with three or more sp2 atoms next to each other. So you're going to call any molecule or ion having three or more sp2 atoms next to one another a delocalized system. And you can see how in any delocalized system, a single Lewis structure fails to really give us the real structure of such delocalized system. So there is a problem here. There is a failure of the Lewis structures that we have been studying so far, because a single one of them is really not giving us the much needed accurate representation of the electronic structures and the bonds of these molecules. Okay. Okay. So sure. So and I'm happy to go over that, because I really need that everybody follows this. Now, this structure is just showing the orbital analysis that we just did. We assigned hybridization to these three atoms. We understood where each lone pair and bonds were residing, and based on that, we concluded that there was a p orbital here, a p orbital here, and a p orbital here. This is the reality of the molecule. Okay, I'm gonna put it over here. This is the orbital analysis of our molecule. This is the real thing. From this orbital analysis, but this is not a structure, this is not a line and angle notation or anything. This is just an orbital analysis that I'm making with you guys, right? We don't draw molecules like this. This is not a notation. Okay, so from this analysis, I can tell that there is pi bond here character and there is pi bond character here. What I mean by that is that there is side-by-side overlapping here. There is side-by-side overlapping here. We define that as a pi bond. And in the single Lewis structure that I presented to you guys, it only shows a pi bond between these two atoms, though there is zero indication in this structure that there is certain pi bond character in between these two, that there is a side-by-side overlapping of these two p orbitals. No indication in this structure whatsoever. So that is missing. And because that is missing, then we can conclude that obviously this single Lewis structure is not an accurate representation of the real electronic structure of this molecule. Okay? So I'm introducing an idea now, which is this problem will be found in any delocalized system. Any molecule which is a delocalized system will face the same problem. A single Lewis structure will not show the real and accurate representation of this molecule. I'm going to give you another example so you can understand this better. So I just show here two different molecules. So I want you guys to first thing first, I want to assign hybridization to these four carbon atoms. What's the hybridization of these four carbon atoms, guys? What's the hybridization of these four carbon atoms? It's the same for all of them. All these carbon atoms are sp2 hybridized. That is correct. Okay. So an sp2 hybridized carbon means once again 3 sp2 hybrid orbitals and 1 p pure p orbitals, right? How many sigma bonds do we have in this carbon? How many sigma bonds there? Anybody else? How many sigma bonds in this carbon? 5 sigma bonds. A carbon can only have 4 bonds. How many sigma bonds? 3 sigma bonds, right? 2 to the oxygen and 1 to the carbon. 3 sigma bonds. So we have 3 sp2 hybrid orbitals, 3 sigma bonds. So the fourth orbital is a pure p orbital for the pi bond, right? How many sigma bonds in this carbon here? 3 sigma bonds. Once again, sp2 hybridized 3 sigma bonds, 3 sp2 hybrid orbitals. The 4 orbital is a pure p orbital, right? And the same applies to the rest. So you can see how in this molecule we do have 4 carbons that are sp2 hybridized, right, next to each other, and each one of them will have a pure p orbital. Okay. Now my question is, in this Lewis structure that I'm showing here, you can see how these two are next to each other, these two are next to each other, these two are next to each other, right? So I must have double bond in all these sections. In this single Lewis structure, I don't see any indication at all of any double bond character in between these two carbons. It's not showing, okay? I only see a single bond there. When I do my orbital analysis, I can see how I have 2 p orbitals next to each other. Okay, is this a delocalized system? Is this a delocalized system? And the answer is yes. It has 4 sp2 carbons next to each other. And we said any molecule or ion with 3 or more sp2 hybridized atoms next to each other, properly aligned, the molecule will be a delocalized system. And you can see how this is another example of a delocalized system in which a single Lewis structure is failing to show what's happening in between these two carbons. Therefore, a single Lewis structure is not good enough to show the real structure of these molecules. Once again, we have a problem for the localized system. How about this molecule? What is the hybridization, for example, in this new molecule? What is the hybridization of this carbon and the hybridization of this carbon in this molecule? These two carbons are sp2 hybridized, that is correct. Okay, and what about this carbon over here? What's the hybridization of this carbon? So no pi bonds in that carbon. That carbon is indeed sp3 hybridized. What about the next carbon, the one on the right side of this one? This one here, what's the hybridization of this carbon? That's also sp3 hybridized. Once again, no pi bonds here, so that's an sp3 hybridized carbon. And obviously these two will also be sp2 hybridized, okay? So everybody understands that. So now let's draw the orbital picture of this molecule. So when I look at the orbital picture of this molecule, I can see how I do have a situation in which, once again, the carbons 1 and 2 on the left side do have a p orbital each because they are sp2 hybridized. Nothing, no p orbital here because it's sp3, no p orbital here because it's sp3, or another p orbital here, another p orbital here, okay? So is this a delocalized system? Is this molecule a delocalized system? So that is correct. The molecule is not a delocalized system because the maximum number of sp2 atoms that we have next to each other is 2, and we need 3 or more. So once again, if you compare these two diagrams, right, these two representations, in this Lewis structure, I see pi bonding between these two carbons, which is the overlapping of these two p orbitals, and there is nothing shown here, but it's really, there is nothing here either. So this is accurate. Here, same thing, right? Here, same thing. So really, a single Lewis structure does show for molecules that are not delocalized the real electronic structure of those molecules. So we don't have a problem with systems that are not delocalized. A single Lewis structure will really show every interaction of pi electrons. But in any delocalized systems, there is always going to be a lacking of showing the real structure and the real interactions in between the p electrons, the pi electrons, the p orbitals with a single Lewis structure. Okay, and that's going to apply, and I could show you any system, any delocalized system will show the same problem. A single Lewis structure will not be enough to show the real structure of these molecules, okay? Because of that, we need to come up with a solution to that problem, a solution to show the real structure of the localized system. And that solution, we call it resonance theory, okay? So guys, I want everybody to understand that resonance theory is not science. It's simply a language, a notation, a new notation that we are going to be using to show the real structure of the localized molecules. Just to clarify, if there is a question, the Lewis structure does not match the orbital analysis only exactly, Ninette. That's exactly what it is. The orbital analysis, and when I said the orbital analysis is what we are thinking is about the real electronic structure of these molecules, right? Which can only be understood if you have a real good picture of the orbitals analysis, okay? So for the localized system, a single Lewis structure is not going to show the real electronic structure of that molecule. Never. For localized system, that's not a problem. A single one will do it. So we don't have a problem with that. That's totally okay. But when we have the localized ions or molecules, that becomes in a problem because a single Lewis structure is clearly lacking to show interactions in between p orbitals. There are some interactions that are not shown in a single Lewis structure. We are missing that, and that's a problem. So because of that, we are coming once again with something called resonance theory, which is the solution to this problem. And the solution to the problem is, instead of showing a single Lewis structure, we are going to show several Lewis structures, okay, as many as needed. I'll tell you how many do you need now, okay, because that will depend on how many on the molecule in particular. So the point is, we will use more than one Lewis structure, more than one Lewis structure to show the real structure of that delocalized molecule or ion. That's gonna be the solution, using, instead of one, using several. It could be two, it could be three, it could be six, depending on the molecule that we on the delocalized system. Okay, that's the solution. And then we are going to say, I'm drawing three as an example here, but as I said, it could be more, it could be less. It's more than one, okay? And then we're gonna place these Lewis structures in brackets, okay? And we are gonna say, we're gonna relate these structures, and this is very important, by this double-headed arrow, okay? Guys, Uh, the real structure, and I'm going to just write it over here right now. The real structure is a hybrid of A, B, and C. There is only one real structure, just one. Okay? And it's a combination of A, B, and C, which means that, and this is extremely relevant, uh, thus A, B, and C, I'm going to use capital letter, does not exist. They don't exist. Okay? So I'm going to repeat this idea because this is very important. So once again, for the delocalized system, we just learned, and I show you examples of how a single Lewis structure fails to give you the real structure of that delocalized system, of that delocalized molecular ion. Because a single one of them is not enough. The solution to the problem is using several Lewis structures. Okay? We're going to use several Lewis structures. We're going to relate them by this symbol here. And we will say that the real structure will be a hybrid of all these structures, a combination of all of them. There is only one real structure, is that hybrid. Therefore, it is extremely important for you guys to understand that neither A nor B or C exist. They don't exist. Only one thing exists, which is one molecule, the hybrid, the combination of A, B, and C. And I'm emphasizing this because this is probably one of the most important thing about this language. Guys, if you see in, I'm sure you've seen in Gen Chem, I'm gonna show you here something like this. So if I write here A and B, okay, you've seen this in general chemistry. What exactly can you interpret from this symbol that I use here? So if you see this in A and B, everybody knows from general chemistry that this means an equilibrium between A and B, meaning that both A and B exist. They are both in equilibrium in solution. Okay, so I'm going to write it over here. That's an equilibrium, which I've seen in general chemistry a million times. So meaning that these two molecules, A and B, coexist in solution, okay? That's the symbology, that's the nomenclature used for in chemistry to show equilibrium in between in reactions from reactants to products, okay? Now, in this new language that we are learning right now, we are using a different symbol, different language, meaning that we're using a double-headed arrow here, okay? And as soon as we use this different notation, it's a different symbol. Once again, it means these A and B are resonance structures. They don't exist. Okay, only one thing exists, which is the combination, the hybrid of both of them. That's the number one thing that I want you guys to know. Number one, what is resonance? So why is resonance something in the first place? Because there are molecules which are we label as delocalized molecules or ions for which a single Lewis structure is not enough to show the real structure of these molecules. All right? Because of that, the solution to this problem is to use several Lewis structures. And we will say that the real structure is a hybrid, a combination of all of them. And we show that on paper but by using these symbols here, the double-headed arrow here, okay, which is quite different to an equilibrium arrows, which are shown here. You see equilibrium in between A and B, both A and B exist, they coexist in solution in a given percentage. It doesn't matter, it depends on the example, but they both exist. You have both of them in solution. When you use this symbol here, you're talking about resonance structures. So everybody must know that that actually means that neither A nor B exist. The real structure is only one, which is a combination, a hybrid of A and B. Okay? So that's what I'm taking the time to emphasize of it. Is there any question so far in regards to this? And please feel free to ask, because I don't want to keep going unless everybody is really clear about this idea. No questions? Okay, guys. So the next thing to discuss here is how are we going to do all these structures? How this is what I said, the language of resonance. Okay. So now we agree that for any delocalized system, we need to use more than one structure. We're going to relate them by this double-headed arrow. So how can we build those structures? So to build those structures, we're going to show, we're going to work on starting from one structure, let's say structure A, and then we're going to show the flow of electrons, of pi electrons from A to the next structure B. Okay. So we're going to show the flow of pi electrons to go from one structure to the next. And we will do that by using the curve arrow symbolism. So the curve arrow symbolism is using just a curve arrow as is shown here. Once again, this arrow will be used to show the flow of pi electrons from one structure to the next. So these arrows will always be, and this is so important, guys, because you're going to be using this every single day next semester, not only for resonance, but for reaction mechanisms. Okay. So these arrows are going to depart always from electron sources. Okay. So what kind of is this? In this case, for resonance, the curve arrows are shown to use the flow of pi electrons from one structure to the other. So if the arrow is departing from electron sources, and we are talking about pi electrons, what kind of electron sources can you guys think of? Please type it in the chat. What kind of electron sources you could potentially think about? Lone pairs is a source of electrons. That's a good answer. What else? What else could be a source of electrons? No, we're talking about pi bonds, only pi electrons. So sigma bonds cannot be involved because those electrons are not flowing from one structure. So in the localized system, we are only worried about pi electrons that are interacting that are not showing a single Lewis structure. So in addition to lone pairs, which could be in p orbitals, and that could be pi electrons. What other electron sources could you think of? Come on, guys. Any ideas? Look at the molecules here, guys. So look at this molecule. So besides lone pairs, what other electron sources can you think of? Pi bonds. So that's it. Pi bonds. So we're talking about electrons in p orbitals. Okay. The only source of electrons for electrons in p orbitals could be lone pairs and pi bonds. So that's electron sources. So you only depart these arrows from lone pairs and pi bonds. Okay, and they will be ending in either a new bond, a new pi bond, or a new lone pair. Same thing. Okay, so I'm gonna give you the example. So once again, I'm gonna go back to the example that we just discussed. Type it over here. This is the example that, as I just mentioned, in which we agree that a single Lewis structure was not good enough to show the real. So now you'll see the answer to the second question that you will ask yourself. So first, whenever you look at the molecule for now on, the first question you need to answer is this a delocalized system? And if the question is a question, if the answer to the question is yes, it is, then obviously you need to use resonance theory to show the real structure of this molecule. Okay. So my suggestion is once you determine that this is the delocalized system, then draw the orbital picture, particularly the p orbital picture of that molecule. Okay. So once I have my p orbital picture of the molecule, I can tell that there is here an area in which I don't see in that single Lewis structure that I have there any indication of pi bonds. Okay, therefore, I need to show another structure indicating that here, and I'm going to color code this as red, there is an interaction in between these two p orbitals because that is missing. And as soon as I show that, I know that that will be enough to show the real structure of this delocalized molecule. So I'm going to add here my double-headed arrow before I draw my next look structure. The second thing that I'm going to do is after this, I'm going to draw all my sigma bonds and the atoms because that is not going to change. Okay, sigma bonds and atoms are not changing. Pi bonds, they do change. Okay, so not changing pi bonds or atoms. Okay, so this is the temperature of a molecule, an oxygen here and an oxygen here. And now I'm gonna think, so I need to show double bond character here. I need to show interaction between these two p orbitals. So what I'm gonna do is I'm gonna just draw a curved arrow from the lone pair here in the oxygen toward this bond. So that's indicating that this lone pair, which is in the p orbital, is forming a pi bond with this carbon. So that's why the arrow is ending in this point here, indicating a new double bond being formed. If that happens, this oxygen has a hydrogen. Now, if I'm using a lone pair for the new pi bond, clearly I will have only one lone pair. And now my question is, what is the formal charge of that oxygen? Anybody knows? What's the formal charge of that oxygen now? So the formal charge of that oxygen, 7. So what's the formal charge of this oxygen, guys? How do we calculate formal charge? I'm gonna pause question. If you guys, I'm not sure if you guys are paying attention. because I see everybody is so quiet. So let me ask this question. What's the formal charge of that oxygen? Please answer the question. So what's the formal charge of this oxygen? The red oxygen. What's the formal charge of that? Okay, so most people seem to know, well, that the formal charge is obviously +1. Remember how we reasoned this before? Oxygen is in group 6, 6 electrons in the valence shell. There are 3 bonds in this oxygen, that 3 electrons. A lone pair is 2, 5 electrons, so it's lacking 1 electron, that's a +1 charge, okay? So once again, I'm showing the flow of these 2 electrons which are in a p orbital over here to form a pi bond to account for this interaction here that is missing. If I do that, obviously this carbon cannot have 5 bonds, so I need to break a bond here, which is going to be obviously the pi bond, because we are showing here the flow of pi electrons. So the pi bond is going to come over here. Departing, once again, the arrow is departing from electron source. In this case, the electron source is a pi bond. Before it was a lone pair, and if that happens, if that happens, then I'll have 3 lone pairs in that oxygen. And if I have 3 lone pairs in that oxygen obviously will be negatively charged. So why get resonant accord if it creates formal charges in an alternative structure when there is no formal charge in the first structure? David, resonance is not resonance does not exist. Okay, so these formal charges are only indicating the electronic distribution of the molecule. Remember that one thing that exists is a hybrid of these 2 structures, is to show that there is double bond character here too. And by reading the information given in resonance structure, you will also be able to tell later on where is where do you have electron density areas that are rich and electron density areas that are putting electrons. Okay, that's what the formal charge indicates here. It's electron density. So what this is telling you is that the real structure is a hybrid of these 2, and over this oxygen here on top, there is an excess of electrons. There is an excess of electron density, and the opposite on the bottom. Okay, that's what it's telling you. Okay, guys. So the real structure of this molecule that I drew is a combination of these 2. Now, the one thing that you need to know, and you will learn more about this in the next semester, is that not all resonance structures will contribute equally to the hybrid. Okay, some structures will contribute uh, higher to the hybrid than others. That means basically that the real structure will resemble more some resonance structures than others. They don't contribute equal to the hybrid. Okay, and there are rules and concepts to learn which one will contribute more. And I'm gonna go into that right now, because first I want you guys to really know the language here. Now to go from this structure to the one on top, then obviously you will have to bring this lone pair over here to form the pi bond, and this lone pair you will have to bring it to the oxygen to break that pi bond, and then the formal charge will be back to neutral. Okay, any questions? Okay, David, these molecules do not exist. This doesn't exist. And this doesn't exist. Okay? So it's not that this molecule is forming something that prefers a former charge because doesn't exist at all. In a molecule, you have an electronic distribution in the one molecule that exists. There is an electronic distribution, and that electronic distribution makes some area of the molecule to have an excess of electron density and some areas of the molecule to have a deficit in electron density. That's all what it is. And you show that by means of resonance structure, but this is just a language. This structure does not exist. And this structure here does not exist at all. Okay, the real structure is a combination of these two that resembles more this one over here. And the former charge has only indicated that in the real structure, the oxygen on top here, the carbonylic oxygen, is richer in electrons than the hydroxylic oxygen. That's all what it's saying. There is no former charge whatsoever because this does not exist. Is that clear now? So when you look at a single Lewis structure and you see the former charges, you can think, okay, this structure will contribute less. But keep in mind that that structure does not exist in the first place. Okay, I'll give you another example now so you can understand what I mean better. And you will see how useful could be resonance structure for how you can use this information of the former charges. Okay, so let's look at this molecule here, guys. Okay, I'm gonna ask a question here quickly. Which is this molecule a delocalized system? So is that molecule a delocalized system? When you answer that question. So definition of a delocalized system is any molecule having three or more sp2 atoms next to each other. Okay. So 10 more people to answer that question. Is that molecule a delocalized system? Okay, so um, large number of people answered the question right. It is a delocalized system. So to answer that question, I will need to assign hybridization here. What's the hybridization of these two carbons, guys? What's the hybridization of these two atoms? So those two atoms are sp2 hybridized, right? Both of them. There is a pi bond, so therefore they must be both of them sp2 hybridized atoms. Okay. So what's the hybridization of this carbon here? That carbon is also sp2. It also have a pi bond. Remember, whenever you see a pi bond, quickly you can assign sp2 because you know that one p orbital is used for that pi bond. Only three can be hybridized as sp2 hybridization, and the same applies for this oxygen, right? So this is simply another sp2 hybridized atom. Okay, so I have four sp2 hybridized atoms in a row. Therefore, this is indeed a delocalized system. I'm going to draw the p orbitals. sp2 is one p orbital, so it's one here. I'm sorry. So there is one p orbital here, one p orbital here, another p orbital here, and another p orbital here. Okay, four p orbitals next to each other, properly aligned. Okay, so if I look at my molecule, I can see how in my original Lewis structure, the moment I know it's a delocalized system, I know that a single Lewis structure is not good enough. Okay, that's my first point. Therefore, I need to use more than the Lewis structure to show the real structure of this molecule. So I need to use resonance theory to account for that. Okay, so here it is. In the real structure, I see a pi bond here. If it's localized, Ruth, so let me give you an example so you answer the question yourself. Is this molecule a delocalized system, guys? This one over here. This is not delocalized because there is an sp3 atom right here. Okay, there is an sp3 atom right there. Therefore, I don't have three or more. Two sp2 here, but the next is sp3. Two sp2 here, the next is sp3, sp3 here. So no delocalization here. Therefore, obviously, a single Lewis structure is good enough. That's it. I don't have to do anything. When I do have a delocalized system, like in this case, then I know that a single Lewis structure is not good enough to show the real structure of this molecule. I'm going to copy paste again this here. So you can see from the orbital picture of this molecule, I see two p orbitals next to each other here, and I see a pi bond. That's okay, right? By next, I have two p orbitals next to each other. So I should be finding in my structure any indication of pi bond, which I don't have. Right here is missing, is lacking, so that needs to be shown. Okay, so it's missing that, and I see these two and I see a pi bond here, so that's good. So I need to show a structure, an additional resonance structure that accounts for this p interaction over here, the pi bond over here. It's not shown. I need a new structure, okay, which we are going to make right now. So as I said, we're going to then build the resonance structure for this. The moment I know that, the moment I understand this is delocalized and it's more than one structure, I'm going to add my double-headed arrow to begin with. Next, guys, remember, I'm going to draw my sigma bonds only. Those are the steps that I'm asking you to follow, just sigma bonds. Because in this structure, we're going to be flowing the pi electrons to get to the next structure. So I'm not going to be worrying about anything else that the sigma bonds right now. And now I'm going to flow the pi electrons from the top structure to the bottom structure to show double bond here, because that is my purpose, to show a double bond here. So how do I need to push the arrows to get a double bond here? So I'll push the arrows in this case, and I explain why, from this double bond over here, okay, to show this double bond. The moment I do this, what's going to happen with this carbon on the left? What's going to happen with that carbon? Nobody knows? No one knows. What's going to happen with the carbon on the left? If I move the double bond to the right, what's going to happen with the carbon right here, guys? It's going to be with a +1 charge because I broke a bond, and it was left with 3 bonds. So therefore, this carbon is going to be positively charged, formal charge +1. Okay, And if I do this, I need to break this double bond, obviously, because this carbon can have 5 bonds. And then, obviously, I have to send this double bond here to the oxygen. Okay? So the oxygen had 2 lone pairs, and now I'm adding a third lone pair because I'm moving the pi bond to the oxygen. And if I do move the third lone pair to the oxygen, once again, guys, the oxygen, sorry, what's going to happen with that oxygen now? So once again, I'm showing a new structure to show double bond character here. So I move this double bond over here to show the double bond character here. The moment I do this, this carbon is left positively charged. Then I need to move, obviously, this double bond over here to the oxygen because a carbon cannot have 5 bonds. So this oxygen with 3 lone pairs, what happened with this oxygen? It's going to have a formal charge of -1. Okay, and that is going to be my 2 resonance structures. How do I know that I don't need any other structures? Because when I did my analysis here, I determined that I was only missing the double bond character at this position. Therefore, I just need to show a structure showing double bond in that position because that's what is missing. If I have that structure, I am done. Now, other thing that I want to clarify, you could think or ask now, why am I moving this double bond over here and not this double bond from the carbon over here? Because if you move this double bond over here, you're gonna be leaving the oxygen positively charged. And oxygen is highly electronegative. You don't want to leave ever in resonance a highly electronegative atom with a positive charge. Sometimes you can get a positive oxygen, but not because you're moving a pi bond to a third atom. So you never do that. It's too electronegative to do that, okay? It's a lot, make a lot more sense to move from the carbon, which is much less electronegative than the oxygen. So the real structure of this molecule is a hybrid of these two, okay? I'm gonna show you now what I mean by that. And that is going to clarify also David's concerns about the formal charges. Remember, once again, this does not exist. So the real structure is going to look like more or less, I'm going to try to do a drawing of the real structure. So you can see what I mean by that. So there is double bond character here in that structure. There is double bond character here. And there is double bond character here. Okay, in my structure. So the pi electrons are flowing in this area over here. 1 second, okay? That's what we mean by delocalization. There is delocalization of pi electrons in all this area. And according to my picture, I see that this carbon over here is electron deficient and this oxygen is electron rich. So I'm going to show that too in my structure. Looking for the symbol right now. Give me 1 second. So I'm going to show in my structures the electron densities that I can conclude the real structure has, okay? Which is that conclusion, I reached that conclusion from my resonance structures. That's what allows me to conclude such thing, okay? So I have a carbon electron deficient here. I have an oxygen which is electron rich over here. And that is the real structure of this molecule, guys. Let me fix this. Give me 1 second. So the real structure of this molecule is not this loose structure, it's this. It's a molecule in which the pi electrons are delocalized in this area, and this delocalization, because oxygen is highly electronegative, will show higher area of electron density of the oxygen and a carbon here that is electron deficient. Okay, that's the hybrid of these two. That's what resonance, and I'll tell you now how can you use that information. So Ryan, go ahead. You had a question. Ryan? Okay, because somebody raised the hand. I don't know if it was you. If anybody had have a question, please feel free to ask. Okay. Okay, so Tammy, that's a great question because I'm going to do this just to answer your question because, okay, so if we were to do so, we will be showing a double bond here and then an oxygen which is positively charged. And what would be the formal charge of this oxygen? Tammy, if you could please tell me. No, do the math. How many bonds do you see in this oxygen? So the charge, okay, so the charge here, 6 electrons in the valence shell, 1 bond, 1 electron, plus 4 is 5, so plus 1, right? And this carbon will be in -1. So what I can say to you is, if you draw this in an exam, will that make sense? Will I say you this is totally wrong? Well, you can draw it if you want, but the contribution of that structure is meaningless. It doesn't contribute pretty much anything. Why? Because you have a carbon negatively charged, so with an octet, an incomplete octet here, and an oxygen which is positively charged and it's highly electronegative. You don't want highly electronegative atom positively charged unless they have a full octet. This oxygen doesn't even have a full octet, so it's a really ugly structure. No full octet and positively charged. Okay, that's why you don't do it. Oxygen is too electronegative for that. Okay. Okay, guys, so once again, so from a carbonyl, you never please, and then just remember this, from a carbonyl functional group, which is the only case in which you're going to find this, from a carbonyl functional group, never move the pi bond to the side because that's not good. It's not going to happen. That's not going to show any kind of relevant delocalization, okay? So, David, I'm going to explain something to you. Remember how I said about formal charges, right? Based on the formal charges of this structure, I reached to this conclusion that the real structure is a system which is delocalized over here, all the pi electrons, with this carbon electron deficient and this oxygen electron rich. And I can only conclude this out of this structure. Even though this is not the major contributor, it does indicate to me the electron deficiency in this carbon and the excess of electron density in this oxygen. And why is that relevant? Because if I add, look at the structure here before you guys knew resonance. If you just look at this structure, at the single loose structure, which is not an accurate representation, once again, because this is delocalized, you could never tell ever that this carbon is electron deficient and this oxygen is electron rich. Nothing here indicates that. Okay, why not? Because once again, that structure is not enough to show the real structure of this molecule. Okay, now how can this information be used? So you can think, if I add a molecule that is negatively charged, if I react a molecule negatively charged to this molecule here, and I'm gonna label the carbons because I'm gonna ask this question now. Okay, so this is carbon 1, this is gonna be 2, this is gonna be 3, and this is gonna be 4. So if I add a molecule that is negatively charged to this molecule here, where, and I'm gonna pose this question, where will this species react? Where in the molecule? In which position? 1, 2, 3, or 4? The reaction will take place. Okay, so if I react a molecule negatively charged, at which position of this molecule with this negatively charged molecule will be attacking? It's negatively charged, and look at the electronic structure of my molecule based on our resonance theory analysis. Okay, the answer is very mixed, so keep Peter's finishing, please. So at which position in this molecule will a molecule reaching electrons will react? 1, 2, 3, or 4? Obviously, it's not going to react to the oxygen because we just concluded that the oxygen has electron density over it. So there is no point for something negative to go over something negatively charged. That's why I didn't even mention the oxygen. Okay, so guys, this is the hybrid of this molecule. Okay, this is the real structure of this molecule. You can see it's a combination of these two. So if I add something negatively charged, that something negatively charged is gonna go wherever there is more electron deficiency, plus goes to minus and vice versa. So the position that is more electron deficient is this carbon over here, carbon 1. So something negatively charged will be attacking carbon 1. Why? Because that's a carbon showing in the structure of this delocalized molecule, that's a carbon that is more electron deficient, and therefore will be the first to react with a molecule that is electron rich. And you can only tell that analysis, you can only reach to that conclusion if you can draw resonance structure and you can interpret resonance structures properly. Okay, that's why it's so important. So once again, this is a delocalized system, so we need more than one structure to show the real structure, the real electronic structure of such delocalized system. We went through coming up with a structure in which we needed to show double bond character here, okay? And I explained why we will move this double bond here, and then we have to break this one here, leading to that structure. So the real one is a hybrid of these two. And that is indicating to me that there is electron delocalization all over this area. So double bond character in these three areas, here, here, and here. And that leads also to an electron deficiency here in this N carbon and an electron rich area on the oxygen. Based on this, I can predict that if I add something negatively charged, that something negatively charged is going to add to carbon number one because it's the carbon that is electron deficient, because that is the real electronic structure of such molecule. Any questions, guys, in regards to this? Okay, I'm going to give you another example. You guys are very quiet today, and which is not good because I think you should have a lot of questions, I'm sure. So if you don't, if you have questions, type it on the chat, raise your hand, feel free, okay? Okay, guys, so I'm gonna give you something else that I think is important for you to know, and is the following. And I'm gonna build on the idea that I just showed right now. Okay. Okay, how do we call this ion here? Anybody remember how do we call that ion? No one remembers that? The positive charge on a carbon is a carbocation. That's correct, Anastasia. Thank you for that. So the positive charge on a carbon, that's a carbocation. Okay? Okay, guys. So I'm going to ask another question. How many sigma bonds do we have in this carbon? It's positively charged. How many sigma bonds do we have in this carbon? There is a total of 3 sigma bonds, right? 2 sigma bonds to each carbon on the left and the right, and there is an extra sigma bond to a hydrogen that it doesn't need to be shown on the screen, and we know that because it's positively charged. Okay, so this is the real structure of that carbocation, right? It has 3 sigma bonds, 2 R's to carbons, and one, once again, to a hydrogen. Okay, so guys, 3 sigma bonds, meaning that there are 3 areas of electron density around this carbon. One area here, sigma bond, another area here, another sigma bond, and another area here, another sigma bond, meaning 3 clouds of electrons around this carbon. The lower energy geometry for 3 clouds of electrons is trigonal planar, right? So that's a way to keep them the farther away from each other, trigonal planar, so with an angle of 120 degrees in between each sigma bonds, right? So any carbocation, guys, any carbocation, this is very important for you to remember. Carbocations are always, we will consider them as sp2 hybridized carbons, okay? And what they have is 3 sigma bonds, 3 sp2 hybrid orbitals, and the 4th orbital, because it's sp2 hybridized, the 4th orbital is also a p orbital, and that p orbital is empty. That's why the carbocation is positively charged. I'm gonna say here empty p orbital. So I want you guys to keep this in mind. It's very important to remember this, empty p orbital. So any carbocation, once again, will be sp2 hybridized. Okay, sp2 hybridized. Because it's sp2 hybridized, and carbocations will always have 3 sigma bonds. We can think about the 3 sigma bonds with 3 sp2 hybrid orbitals. And the 4th orbital is a p orbital, as in any sp2 hybridized atom. But in this case, the p orbital is empty. That's why the carbon is positively charged. It only has 3 bonds and an empty p orbital. Okay? So with that in mind, I'm going to ask another question here. And the question is the carbocation shown is that carbocation, a delocalized ion. So is the carbocation that is showing on the screen, is that a delocalized ion? And once again, we define the delocalized ion as an ion having 3 or more sp2 atoms next to each other. So to determine if it's delocalized, you need to first and foremost measure and assign hybridization to the atoms. Okay. Okay, guys, come on, finish answering the question. Is a carbocation a delocalized ion? Okay, so 11 people are not answering the question. I'll take note of that later on because people are clearly not, probably not paying attention. So what's the hybridization of this carbon here? And what's the hybridization on this carbon here, guys? What's the hybridization of these two carbons? So those two carbons are clearly what? sp2, right? So that's sp2. What about the carbocation? What's the hybridization of the carbocation? We just discussed that. Carbocation will be considered as sp2 hybridized. And what about these two? These two carbons? sp2 as well, right? So clearly, this is indeed a delocalized system because we have, in this case, 5 sp2 carbons next to each other. I'm gonna draw once again my orbital picture, and I suggest you guys to do this every single time, especially when you're learning this, so you know what to do, right? So I have 5 sp2 carbons, right? 5 p orbitals next to each other. Okay, the only difference is that this one is empty. How many pi electrons do I have in this system, guys? How many pi electrons do we have in this carbocation? This is a delocalized system. We just agree on that. How many pi electrons in this delocalized system? So that is 4 pi electrons, 2 in this sigma bond, another 2 in this sigma bond, that's 4. This p is empty. 4 pi electrons, right? Okay, so this is the orbital picture. I can see 5 p orbitals. I see a double bond in this Lewis structure showing interaction in between these two p orbitals, so that's okay. I see a double bond in the Lewis structure showing interaction in between these two, but here I see sigma bonds, single bonds, and here as well. So clearly, I don't have anything in that structure indicating double bond character here, and I don't have anything in that structure indicating double bond character here. Okay, so I need to show resonance structures that account for the interaction, the delocalization in between these two carbons, and interaction or delocalization in between these two carbons. Okay, guys, so how many resonance structures do I need? So how many? So I need two resonance structures. Okay, guys. So two resonance structures, one showing double bond here. So if I show double bond there, clearly by using this curved arrow, this carbon here is going to be left with three bonds. So this carbon is going to be positively charged. Okay. And the second structure is going to show double bond in the blue bond because that is also missing. Okay, so I'm going to color code the curve arrow so you guys know what I'm doing. So this is to show the double bond here. This one is to show the double bond on the other side, okay? So if I'm moving this double bond here, then obviously I have a double bond right here, and then the right carbon will be positively charged, okay? So with two resonance structures, I'm showing the real structure of this carbocation. This carbocation is a hybrid of these three structures, okay? A hybrid of these three structures, meaning that I'm gonna try to draw you guys what the hybrid means, okay? Especially at the very beginning when you're learning this, this might be pretty helpful. So it means that there is delocalization all over this area. Okay, and it also shows that there is electron deficiency in this carbon here, in this carbon here, and in this carbon here, because so the positive charge is shared between carbons 1, 3, and 5. So guys, if this carbocation, which is electron deficient, okay, has 6 electrons in the valence shell, carbocations are highly unstable. Obviously, they have 6 electrons in the valence shell, so highly unstable. Okay, 6 electrons in the valence shell, meaning that they will react quickly with any species bringing 2 electrons. Why is that? Because it has an empty p orbital to accept these 2 electrons and complete 8 electrons in the valence shell. So carbocations will react with electrons that are electron rich. And if you mix a carbocation with an electron rich species, that carbocation will react at positions 1, 3, and 5. So you will get 3 products because you have 3 carbons that are equally sharing the electron deficiency in this carbocation. And that's once again one of the reasons why resonance is so relevant, because it not only gives you the exact and accurate electronic structure of these ions, but it also helps you to predict how and where these ions or molecules will react. So there is a question here. So there are 3 or 2 resonance structures in that example. How many resonance structures do you see in this example? Nina, total. There are 3 resonance structures. I gave you one and I asked, is this a delocalized system? You guys, we agreed that it's not, so we needed to add another 2 to show the real structure of this carbocation. The real structure of the carbocation is a hybrid of these 3 structures. And that hybrid accounts for electron deficiency in carbon 1, as in this structure, carbon 3, as in this structure, and carbon 5, as in this structure. This is the real structure of this carbocation. Okay, let me show you this other example very quickly, and this is going to help you to understand something else. Well, I said we needed to add another 2 to the one that we had. Okay, that's what I said. How many do we need to add to this? 2 more, and the total is 3. Okay, guys, what about this structure? So I'm going to ask this question again now that we're ending the class. Let me ask this question. Is that a structure? Is that carbocation a delocalized ion? The one that I am giving you now on in the slide. Is that a delocalized ion? Good. Okay, so remember the localized ion needs 3 or more sp2 atoms next to each other. Okay, so we have sp2 sp2 here. Here this is sp3, no pi bonds here. sp2, but this is sp3, right? So a lot of people did not answer that quickly, but it's not a delocalized ion. So a single structure is enough. Okay, so my question is, it's not delocalized. Another way to ask this question could be, is this single structure an accurate representation of the real structure of this ion? Is it? It is, because the system is localized. Okay? Guys, and then I want to share with you a last piece of information. So if you compare these 2 carbocations, right, I'm showing the hybrid here, because that's what it really is. If you compare these 2 carbocations, I just said that carbocations are highly unstable because you have a carbon with 6 electrons in the valence shell. Therefore, those carbons are going to be really looking for completing electrons in the valence shell. Okay, so carbocations are highly unstable. So if we compare these 2 carbocations, the one on top and the bottom, do they have the same stability? I want you guys to think. So do these 2 carbocations have the same stability? Do they have the same stability? What do you guys think? So I just said a carbon positively charged is highly unstable because it has only 6 electrons in the valence shell. The carbocation on top has only 1 carbon supporting the entire +1 charge, whereas the one on the bottom has the same +1 charge shared in between 3 carbons. So there is a third of positive charge in each one of them. So the positive charge is shared. Therefore, carbocations that are delocalized are stabilized by resonance. Okay, I'm going to type it on the chat. Carbocations, delocalized carbocations are stabilized by resonance. Okay, why is that? Once again, because in the localized carbocations, the electron efficiency is fully on a single carbon atom, whereas in the delocalized carbocation, the electron efficiency is shared between 2 or more carbon atoms, in this case, 3 of them. So that makes that carbocation way more stable. And this is going to be a very important concept and a very important idea for you guys to know for next semester. Okay? All right, guys. So I'm ending today's class with this idea. So is the bottom one more stable? Yes. The bottom carbocation is delocalized, therefore it's more stable because once again, the electron deficiency, the positive charge, is shared between three carbons, whereas in the top structure, the positive charge is fully on a single carbon. So that makes the one on the bottom more stable. Any other questions, guys, that you might have?